So till now, we have learnt about the basics of what a random variable is. We have learnt what a PDF is, what a CDF is. We also learnt a very popular distribution called the Gaussian distribution or the normal distribution. And we learnt a few properties of the Gaussian distribution, right? Like the 68, 95, 99.7 rule. We learned some of these. The big question here is, okay, all this theory is great. We understood the theory. How to use these distributions in the real world, and where do we use these distributions? These are two very important questions. So let me give you some examples and on how, where, and when to use these distributions, right? So in a nutshell, if I have to tell you in a nutshell, all the probability that we learn, all the concepts in probability, including distributions that we learn, are mostly used for data analysis, right? They help us answer. What is data analysis? Data analysis is all about answering questions about data. It's all about answering questions about data itself. So probability, all the techniques that we learn in this probability chapter are used for exploratory data analysis. And the exploratory data analysis that we do with probability is about answering questions about data. Let's understand this a little more with an example. Okay, let's take a first example, right? So let's take the first example in the question. Imagine you're working at a large corporation, right? Let's assume you're working at a company and the name of the company or organization is XYZ. Let's just say, okay? And your task is to order t-shirts. Your task is to order t-shirts for all employees, right? This is your task. Suppose for some annual event or something, it could be a company or a college or an institution or a university. Imagine we are trying to order t-shirts for all employees or for all students. Now, the big question here is there are multiple sizes of t-shirts. You have small, medium, large, extra large. Now, let's assume you have some 100,000 employees, 100K employees or 100,000 employees, right? Now, question here is, this is a very important question, right? So let's start with question A. How many Excel t-shirts should you order? How many Excel t-shirts should you order? Very valid question. Because if you do not order sufficient shirts, you know you have 100,000 employees in your company. You want everybody to get a t-shirt. If you order too few, there will be many people who won't get the appropriate t-shirt and hence they won't use it. If you order too many, again, most of them will go waste, right? So it's a very valid real world problem, right? How many Excel t-shirts should you order? Now to solve this problem, this is a very, very real world problem. Now, when you want to solve this problem, how do we go ahead about it? One way is to ask all the 100,000 employees. Okay, strategy one is to collect data. For all 100K employees. Okay, that's one way. But this will be too time consuming, lot of time wastage, a lot of people have to give data, right? I mean, you can collect all the data for all the 100K employees, but let's assume the cost of collecting data is too high. Then you come up with an idea. You say that typically people who are taller than 180 centimeters, let's assume you know this, okay, common sense, sort of like common sense or domain knowledge, okay? People who have done this before have told you that typically people who are over 180 centimeters tend to wear an XL size t-shirt. Okay, and they could say if people's heights are between 160 centimeters and 180 centimeters, they tend to wear an L-sized t-shirt. This is not perfect because there could be somebody who is wider and things like that. But roughly this is logical. If you know that people who are within this height range, typically majority of them will use an L-sized t-shirt, and people who are taller than 180 centimeters tend to use an XL sized t-shirt, and so on and so forth. Imagine this is your domain knowledge, right? Again, this is your domain knowledge. that you have obtained from people who have done this before, or just observations about human sizes, about how apparel manufacturers manufacture their t-shirts and stuff like that. Okay, this is domain knowledge. Since collecting data from all the 100K employees is expensive, you would say, let's use this domain knowledge smartly. And the way we will use it is that we will collect heights. We will collect heights of 500 random employees. Let's just say I try to do this. Okay, so I have 500 heights. From these 500 heights, I will try to estimate the mean and standard deviation. I will estimate. I mean, this mean and standard deviation is actually a sample mean and sample standard deviation. It's not the population mean and population standard deviation. But I'm assuming that the sample mean and sample standard deviation are close to. Again, this is an approximation. Okay. Now, if I know, so again, here are the steps. Okay. Again, we are still solving the same problem. My first assumption is that we can determine the size of t-shirts from the heights of people, which is a reasonable thing. And since I can't collect heights of all the 100,000 employees, I am saying let's collect heights of 500 random employees. And this is not impossible, right? You just have whenever at the door of entry, or at the gate of entry to your offices, you randomly filter 500 people and say, could you just give me your height? It will not take us more than 10 seconds to measure it. Okay, very useful. So you got 500 values. Now from these 500 values, you got your mean and standard deviation. Right? Of course, these are sample means and standard deviation, but I'm assuming that my sample mean and standard deviation are roughly close to my population. It's an assumption. It's an approximation actually. Now, if somebody tells me that heights are normally distributed, if somebody tells me that heights are normally distributed, and I already computed my mean and standard deviation, this is the fun part. So I learned, this is very important here. I know that heights are Gaussian distributed. Again, who told me this? It is probably a doctor or a physiologist who studies human physiology, who knows that typically the distribution of heights are normal. And I approximated the population mean and standard deviation using the sample mean and sample standard deviation. There are many ways of doing it. This is one way of approximation, very crude way. Now, given this, I can answer lots of questions, right? Imagine, what is my original question? How many Excel t-shirts should I order? And if I know the sample mean and sample standard deviation, I can compute. Okay, I can easily compute the probability of my heights being greater than equal to 180 centimeters. Because the moment I know the distribution, the moment I know the mean, the moment I know the standard deviation, I can now plot my PDF and also my CDF. Now in my CDF, let's assume these are my heights. In my CDF, now I'll say where is 180 centimeters and what percentage of people are above 180 centimeters. Let's say 1% of people are above 180 centimeters. I can read this from my CDF, because what will my CDF look like? If I look at the CDF of my Gaussian distribution, the CDF looks like this, right? Just the fact that heights are normally distributed, if I know mean and standard deviation, I can plot the CDF. These are my heights. And here I'll say this is corresponding to my 180 centimeters. And corresponding to 180 centimeters, let's assume the CDF value is 99%. Then I know that the probability of heights greater than equal to 180 centimeters is equal to 1%. Which now means that of the 100,000 employees, 1% of these employees will be taller than 180 centimeters, which means 1% of employees would need an Excel size t-shirt. So I'll order roughly 1% of this, which is 1K t-shirts I'll order as Excel t-shirts. Now here we have done lot of assumptions, lot of analysis. First assumption is that you can predict the size of t-shirt from the heights, which is a reasonable commonsensical thing. Next, heights is a Gaussian distributed random variable, and I'm computing the mean and standard deviation using a sample. The very fact that heights are Gaussian distributed will help me get this CDF and all the values in it, right? So in a nutshell, your distributions, like a Gaussian distribution, right? The very fact that heights are Gaussian distributed give us a theoretical model, on the behavior or the distribution of heights itself, right? I can simply plot this CDF the moment I know the mean and standard deviation of heights. So Gaussian distribution is a theoretical model. Gaussian distribution is a theoretical model that is observed in many natural phenomenon. In many natural phenomenon, Gaussian distribution is observed. But the distribution itself is a theoretical model. And the moment I know something is Gaussian distributed, I can make all of these observations and I can answer all of these very, very interesting questions, isn't it? So this is a very real world data analysis question. Probably a lot of people in the HR teams who have to order t-shirts would actually use data like this, right? Similarly, let's now take a slightly different example of where distributions are useful. Let's take a second question. Now let's assume I have salaries of all the employees in a company. Now, the first question, see, remember, the first thing, if salaries are Gaussian distributed, I can answer lots of questions like how many people, how many employees. I can answer questions like how many employees make a salary greater than equal to $100,000. If I know the distribution, if this is a big if here, if your salary is S, is Gaussian distributed with some mean and variance, and if you can estimate, again there are three parts here. First part is that this is Gaussian distributed and I know the mean and I know the standard deviation. As soon as I know this, I can take all of the theoretical model of what a Gaussian distribution is and I can answer questions like this. I can also answer other questions like how many employees make a salary between $50,000 and $70,000. Right? I can again read this from the CDF, right? Imagine if this is a CDF, if this is the CDF, and if this is $50,000 and this is $70,000, and if this value let's say is 0.4, and if this value, right, if this value is 0.7, right, I know that about 30% of points lie between $50,000 and $70,000. Because there are, what is a CDF? Again, this is CDF of salaries, right? I know that 40% of points lie below $50,000 and 70% of employees make less than $70,000. So there are 30% of people or employees who make salaries between $50,000 and $70,000. And all these are very important data analysis questions. All of this is part of your data analysis. And you can answer that if I know that salaries are Gaussian distributed and if I can estimate my mean and standard deviation. Now the big question here is, how do you determine this? The first question here is, of course, you can use sample means and sample standard deviations and all of that. But how do you test that your salaries are normal distributed or not? That's where our QQ plots could help. We have already learned QQ plot, right? If imagine if I have, let's say, salaries of 1,000 employees, 1,000 observations, right? If I have not even 1,000, even if I have 500 observations, I can use the QQ plot to determine if actually salaries are Gaussian distributed or not. Later in the chapter, we'll learn other techniques like KS test to determine if salaries are Gaussian distributed or not. If salaries are not Gaussian distributed, we can't use the CDF. Right? If salaries are Gaussian distributed, very well. Very, very well. No problem. If salaries are not Gaussian distributed, we can't use it. So Gaussian distribution is giving us a theoretical model of the distribution of data. And Gaussian distribution is observed in lots of cases in natural phenomena. There are many other distributions that we'll learn little later in this course, but each of these distributions literally provide us a theoretical model on the distribution of data that we can see from the PDF and CDF. This is the PDF and this is the CDF. The PDFs and CDFs of a random variable X, right, tell us how data is distributed literally. And the theoretical model gives us the, because imagine if I'm observing the same type of PDF and same type of CDF in many things. It makes sense to build a theoretical model which I can reuse multiple times. And if I find some other data to be belonging to Gaussian distribution, I can use all the learnings that I have from the theoretical model, like the 68, 95, 99.7 rule. Right? We got this rule for the Gaussian distribution. Now, if you tell me that any random variable is now Gaussian distributed, I can use the same rule here. So distributions, especially these distributions like Gaussian distribution, are theoretical models of what to expect. What are the properties that this random variable would have if it is following this theoretical model? But of course, it also has applications in data analysis, like the couple of stuff that we have seen, right?